Welcome back, students. In the previous lecture, we learned how do we search for a particular number using divide and conquer strategy. In today's lecture, we will try to find out how to find a maximum and a minimum number in a given set of elements. We will be using two approaches while trying to find out the number. One approach will be using an iterative algorithm, and the second technique will be using divide and conquer strategy. If I look for the straight algorithm, the algorithm for finding a number which is maximum and minimum in a given set of numbers, the algorithm will be like, let's call it algorithm straight maximum, just to make it more comprehensible. So in a given array, this is the array that's given to us with n number of elements, and our job is to find basically the maximum number in this array and a minimum number in this array. The idea behind this algorithm is extremely simple. What we are going to do over here is that we will check for a first number, and then we will keep on comparing this number with the rest of numbers. So in this case, let's call that the first number that I am looking for will be represented by a of 1. If it is the only number in the array, then this is the minimum possible number in the array, and this is also the maximum possible array. But in cases where there are more than one numbers, so we will try to find using an iterative fashion. So we will run a loop from 2 to the last element. Now the job here of this loop is basically to iterate through the array, compare every single element with this element, and if we find out any element which is maximum, which is larger than this particular element, then we will basically store that element in the max variable, and if there is any number which is smaller than this number, then we will store that value in the minimum. How it will work out? So we will check for the conditions. If now let's look for every single number and compare those numbers with this number. Now if a of I in this case is greater than max, remember in the first iteration max is basically holding the value of the first element. Now I am checking for the second element. If that element is greater than the max value, then in that case, if it is true, if a of 2 is greater than the existing value, then we will store a of I in max, and we'll stop here. Now that's for the maximum value. Let's look for the minimum value, and we'll do the similar type of procedure over here. In that case, if my a of I is less than minimum, then I will store that a of I as a of minimum, and we'll stop here. Let's look at how this particular algorithm works. Let's take an example to make you understand how this will work. Let's assume I have a set of numbers. I have a 7, I have a 5, I have a 3, I have a 9. So this is the given set of elements. Let's call this set of elements A, and the value of n in this case is, for this is 1, 2, 3, and 4. So in first example, in the first step, what I will do is that I will take the first element, that's a of 1, and I will store that as max, and the same element I can check out as main. Now the value of a of 1 is in this case 7, and minimum also is 7. Let's try to understand how this loop will work. Now once the loop starts working, the loop here, the loop index is initialized with the value of 2. That means the element is now pointing towards the second element. We'll compare the second element, that's 5, with max. So 5 is basically now a of 2 is equal to 5, and at that a of 5 I'll start comparing it with max. Is this 5 greater than 7? If in case it is greater than 5, which is not true in this case, it's smaller than 5, smaller than 7. If it is true, then in that case we'll store that in max. But since in this case 5 is less than 7, the condition is false, so max will only retain the earlier value that it has of 7. Let's check this 7 for the second condition of minimum values. Now is my a of 7 5 less or equal to 7, which is true in this case. 5 actually is less than 7. So in that case we'll rewrite or overwrite the value of minimum by the new value. So minimum will store a of 2, which is 5. Likewise, we will just iterate through all these possible values till we reach the end of the this array. Once we reach the end of the array, we will exit the loop, and by that time the max will be holding basically the maximum possible value in the array, and the minimum will be holding the minimum possible array. Let's look for the number of comparisons that's going to make. The total number of comparisons there will be 2 into n minus 1. That will be the kind of complexity I'm talking about. We can have an immediate improvisation in these cases. Say, for example, if I see this particular comparison. Now, at one possible time, at every period of time, there is only possibility of one condition being true. So in that case, if I just make use of an else statement, so they will execute basically conditionally. So either one of them will execute at one point of time. That's a slight variation or slight improvisation in the existing algorithm. What we are actually interested in this case is using divide and conquer strategy. So using DNC strategy, we'll try to find out that how do we improvise, or how do we improve the performance of the existing algorithm. Let's first go to the algorithm of DNC, then take an example to understand how exactly it works. After the iterative version, let's have a look at how can we possibly solve this maximum algorithm using divide and conquer strategy. Here given is the algorithm for this strategy. What we will do in this case is that we'll take a parallel example in this case and try to fit that possible example onto this algorithm. Let's briefly try to understand what's happening over here. Say we have two pointers basically that I'm using as I and j. These I and j will be basically pointing towards different, these are more of an index for the array, and will be pointing towards the different elements that represent the array. Again, I'm using these variables max and min. The max here in this case will be storing the largest possible value in the array, and the minimum here will be storing the lowest possible array in the array, lowest possible element in the array, sorry. Now, three cases we'll be looking at in this case. One case wherein we have only a single element in the array. So in that case, both I and j, they are actually pointing towards the same element. If that's our case, something like this, my array contains a single element, so 5. So obviously in this case, 5 is the only maximum possible element in the array, and 5 is also the minimum possible element in the array. So this will be taken by this, this is the case which will be taken care by this part of the algorithm. Second case, let's assume we have two elements in the array. We have 5 and a 7. So for this case, we need to find out which one among them is larger and which one among them is a smaller element. So for that, what we will be doing is that we will be comparing a of I and a of j. So I will be pointing towards this element, and j will be pointing towards this next element. So we will make a comparison between a of I. Now a of I here is 5, and a of j here is 7. We will make a comparison between two, and accordingly, whosoever is larger will be stored in max, and whosoever is smaller will actually be stored in minimum. These are the two base cases, as we learned in binary search algorithm, the divide and conquer strategies, they have base cases. So these are two base cases. That's why I'm basically pointing as a comment over here is the small p case. Let's look at the larger set of the problem. Larger set of problem is that multiple elements can be present basically in your array. How do we actually solve? Let's take an example and try to understand how exactly does this algorithm work on a larger set of problems. Say for example, I have an array which contains elements 27, 13, -1, 5, 9, 11, -7, 4. Let's call this array, it's my array A. To make it more readable, I'll actually put it as isolated elements. Now this is a given array. In this given array, my job over here is to find out which element is the larger element and which element is a smaller element. And once we have done with the algorithm, the max variable should be storing the largest possible value, and the minimum should be stored basically the smallest possible value. Let's look at the algorithm. Now, let me reiterate basically the fact that divide and conquer strategy essentially works on the fact of basically dividing the larger problem into smaller problems. Once we get those small problems small enough, of almost unit size, then we can basically solve the small problem, and then we combine result back. That's exactly what we are going to do over here. This is a larger array. My job over here is to basically divide this into smaller possible arrays. Once I get those smaller possible arrays, then I can basically solve those smaller arrays. These are the small problem cases. These are the cases that fit. Say I can basically divide it onto a level where it's a single element, or I can divide it to a level where there are only two elements. So then using taking help of these cases, I can easily solve a single element array or a 2-element array, and then I can combine those results back and get this job done in this case. So what we will be doing over here is that I need to find out where do I divide. Remember, this is there are some examples, say be it a merge sort or be it this algorithm. In these cases we actually divide it in exactly 2 halves, but we will be also learning some other algorithms like a quicksort algorithm, wherein the division, the partition will not be 2 equal halves. It may or may not be 2 equal halves partition. So let's start out and find out. First thing, the algorithm tells me that if this is the case, that it does not fit a single element, it does not fit 2 elements, then in that case let's start here. Let's compute a mid value. That's exactly what we did also in binary search. So let's find a mid value. Let me try to make it more readable by illustrating it. So mid value, okay, let's find the number of elements, indices. Let's start the array indexing by 1. This is 1, the second element, this is my third element, this is my fourth element, fifth, sixth, seventh, and eighth. I have 8 elements over here in this case. Now, finding out mid, that will be 1 plus 8, that's essentially 9 by 2. Now remember, in these cases, always remember that we basically use those floor functions, so the values will be nearest lower value, which in this case happens to be 4. So 4 is my mid. Once I compute my mid, what we are doing is that we are trying to now divide the problem. Now this is the divide part over here. Now I'm putting these in comments. Let me highlight these. I'm putting, these are comments basically, these are comments, this is a comment. So this is the division part of the array and of the problem, and this is the combined part. Let's first work on the division part of this. The division part says that we make a recursive call back to the same function that we are basically using right now. So when I make the back call, max min, in this case the arguments basically go as I, that will be the first element. I is pointing right now towards the first element, and mid is the newly computed value, that will be 4, and j is pointing towards 8. So here essentially let's write it down. In the first case, I is pointing to 1, j is pointing to 8, and mid is pointing to 4. So when I make this new call, that will be, new call will be like this: 1, 4, and max and min. This is the first call that I am making. But since these are consecutive recursive calls, they will be pushed onto a stack. So I'll also have to push the next immediate call onto a stack. Let me try to basically go just like we did in the last lecture. Let's try to create a tree out of it and find out how exactly will this be represented in the form of a tree. I'll keep on calculating these intermediary values as and when needed. So in the first case, when the first call becomes like over here, my I is 1, so here max min, my I is 1, my j is an 8. The value of max is not known to me yet. That's very important over here, you need to understand. See, these indices, we understand what's the index value of these things, but which value out of these 8 elements is the maximum value, that's yet to be known. That's what we have to discover. So I'll just keep it as max right now for some time, and minimum value also is not known to me. This is the actual problem as it stands. Let's try to apply divide and conquer strategy on this particular algorithm now. When I start dividing it on the first call, see over here max min call, when I make that division on the first call, we can find out that is the starting element, so that will be my I, and my mid in this case is my 4. So essentially I'm actually trying to divide it into these 4 elements. The division will be here. This is the first division I'm trying to create over here in this case. So this is the first half, this is the other half. Then I will try to basically divide this first half into sub-problems and the other half as well into sub-problems, and then we'll try to solve it down. Once we narrow it down to very smaller problems, small set of problems basically. Again, when I divide it over here, 1 and 4, so essentially I'm talking of this half, this subset. Again, the value of maximum and value of minimum is not known to me, so I'll just keep them as the values they are, max and min. They are not known to me, so I'll just keep them over there. Once we basically solve them, once we start combining it back, we'll basically discovering these different values. The second call here is max min. Now we are starting in this case mid plus 1, so up to this it's covered. We need to find out the rest of the elements, so it's mid plus 1. So essentially I will start from 5 and all the way up to 8. Again, in this half, the values of max and min are not known to me. So we'll continue like that, the way it is. Look at these max-min calls. Basically, they are recursive calls. Now we can find out in this case that these are not small enough problems to be solved. So what I will do essentially is that I will try to basically recalculate the new mid value for this half as well as for this half. So the new mid value for this half will be 1 plus 4, that's 5 by 2, that's 2. It's my new mid value. And in this case, the new mid value will be 5 and 8 is a 13. 13 by 2 is essentially 6. This is the other half, right? So let's see the other two recursive calls that will be generated in this case will be 1, that's the ith element, first element, and mid. The new mid in this case is now my 2. Again, the value for max is not known, the value for min is not known. I almost forgot, please let me correct myself over here. The second call over here is interesting. Basically, the second call that's going over here, it's important, let me highlight it. The variable name that I'm using in this case is a max 1. As you can find out, it's not a max like we are using in this case, and it's a min 1. So essentially these are two different variable names I'm using in this case, a max 1 and a min 1. The reason for that being that once I start combining those solutions back, I need to combine it from this half and this half. I need to basically compare these two results and then get the final result. To compare these two results, I'm using two different names. It will be two different storage these holders which will be holding the max and min values. I'll compare them, so that comparison will be possible only when I'm using two different names. I cannot compare with max. So that's why, let me make a correction here. It's max 1 in this case and min 1 in this case, as it's pointed over here. Similarly, in this case, the second call will be mid plus 1 up to final element. Mid plus 1 will be 3 and final element is 4. See here, this is my I, this is my j for this case. In this case, this is my I and this is my j, right? So this is I to mid, this is mid plus 1 to j. 3 and 4, the similar case, max not known to me, min not known to me. I'll keep them as they are. Let's look at the other half of this figure. Now here, let's see, the divisions are 5 and the new computed value of mid is 6. So it's 5 is the initial, 6 is the final element. It's max 1 here and min 1 here. Max and min, and 7 mid plus 1 and 8 max of 1, min of 1. Okay, is this problem small enough that we can actually solve this problem? Let's have a look. Now there are two elements basically that are that we have over here. Now this is essentially the second case wherein we are talking actually I is j minus 1. Now I here is 1, j is here, j here is 2, so that's j minus 1 is 1. So essentially is the case that can fit over here. Let's have a look at a of 1. Now 1 is represented basically this element. So a of 1 for me is a 27. It's very easy, it's very simple basically to understand it from this point of view. If I check my a of 2, now a of 2 is basically pointing towards 13. If you make a comparison between these two, it's self-explanatory that for a of 1 and a of 2, in this case I am comparing a of 1 with a of 2, and a of 2 obviously over here is larger element than a of 2. So whatever I will do is that essentially my max now will store a of 1. My max is now storing a of 1, right? And my minimum is basically in a of 2. We are done with one job. Now remember that recursive tree that I drawn last this lecture, that it works basically something like this. So we start from top and then we move towards and we solve this problem. Once we solve this problem, then we move back and try to solve the other half. When I try to solve the other half, a of 3 here is pointing towards minus 1, and a of 4 in this case is pointing towards 5. if we make the comparisons between a of 3, that's minus 1, and a of 4, that's a 5, when we start making comparisons, we can find out that a of 4 is larger than a of 3 in this case. So 5 is essentially larger than minus 1. So max will be storing, max 1 here will be storing a 5, and min 1 will be storing a minus 1. So this half we are done with. Let's try to combine these two results back. When I start combining these two results back, so this is the combination part over here. The combination part tells me that now this is the max and this is the max 1. This is why I was basically using two different variable names, because I need to now compare this half with this half. So in this combined part, I'm saying that if max 1 is less than maximum 1, max is less than max 1. Max is containing 27 at this point of time, and max 1 is containing 5, which is not true. Max is not less than max 1. So we'll continue max being the existing number, which is basically 27 in this case. Let's also look for the minimum possible value. Is this the minimum value we have? So I'm again using two different names, min and min 1. Is my min greater than min 1? My min currently is storing 13, and my min 1 is currently storing minus 1. That makes the condition true. My min actually is greater than min 1. Since we are looking for the minimum possible values, so now the next, the min 1 basically will now be stored in my min. So max out of these two will be 27, and min out of this min and min 1, the min will be minus 1. Therefore, we solve the first half of the problem. Similarly, let's look at the second half of the problem. In this case, I have element 5, that's a of 5, and a of 6. If I make comparison between a of 5, which is a 9, and a of 6, which is an 11. Once I compare, obvious, it's very obvious in this case that 11 is larger than my 9. So my max will be storing 11, and my min will be storing a 9. Let's look at the other half of the same problem. In this case, a of 7 now is pointing towards a minus 7, and a of 8 is now pointing towards 4. It's very obvious that 4 is the larger value in the two, and minus 7 is the smaller value. So my max 1 will store a 4, and my min 1 will store a minus 7. Again, I will be applying the combined part of the algorithm. In using the combined part of the algorithm, I will be now comparing this half essentially with this half. So let's compare the first two maximum values. The maximum value in the left half carries an 11, and the max 1 in the right half carries a 4. So if I compare this half max with max 1, which I'm making the comparison over here, max, and I'm comparing it with max 1, I can find out easily that 11 is greater than max 1. So the max now will be storing value 11. And in case of minimum, it's also obvious that we have a negative value. Since we have a negative value over there, and the negative value is compared with the 9, so minus 7 out of these two is the minimum value. So essentially we have solved the first half, we have solved the other half. Let's try to combine both results together and solve the entire problem. Now we'll be comparing this half with this half. Now let's compare this max with the max 1. What's the value stored in max 1? Now when I compare this max with max 1, this max is containing a value of 27, while as my max 1 is containing a value of 11. So if I make the necessary comparison, I can find out that 27 is the larger value. And for my minimum values, I'm making a comparison between a minus 1 and a minus 7. So when I make those two comparisons, I can find out that a minus 7 is a smaller value. Thereby, we have solved the entire problem, and we can now claim that my 27 is the max element in the present array, and my minus 7 is the smallest possible element in the array. Dear students, this is exactly how do we solve a maximum minimum problem using a divide and conquer strategy. Next, we'll be having a look at the merge sort problem. Again, the merge sort problem, let me introduce over here. It's a sorting problem, essentially wherein you try to basically sort the numbers. You try to order some numbers that are there available in the given element, given array that are given, or in a given set of elements. But our job over there is to sort those elements in some particular order, particular fashion. It may be an increasing order where the numbers start from smaller towards higher, or it may be a decreasing order wherein we have larger numbers in the beginning and they basically move towards the smaller part of numbers. We'll be learning that lecture. We'll be learning that merge sort in our next lecture. Till then, you take care.